Good afternoon everyone. Today we will continue course Reservoir Geomechanics and we will consider today borehole stability analysis and Reservoir Geomechanics. This is lecture plan for today. The first topic is applied borehole stability analysis. As you can see here, the problem of wellbore stability includes forecasting of circulation losses, mechanical sticking associated with the bottom hole zone damage, hole cleaning, selection of mud weight density, deviation angle analysis, as well as differential sticking associated with a difference on the pore pressure and mud weight. For example, the geomechanical model shown on this slide made it possible to estimate the required safe mud weight window, to identify losses and breakdown zones, and estimate the depths on casing, shoes, landing. The results of geomechanical modeling show that most well instability problems are caused by low mud weight. It's recommended to increase the mud weight in this case are needed and according to the planned wellbore. It can drill wells with an inclination angle below 35 degrees, which is safe and stable. Also, drilling should be parallel to minimum horizontal stress to reduce the risk of instability. Monitoring of ACD, equivalent circulation density, is important to avoid circulation loss of drilling when the upper limit of mud weight is exceeded. Pumping and surge should be monitored and upper and lower mud weight limits set to avoid wellbore instability issues. Ultimately, controlled drilling rate, proper well cleaning and proper mud conditioning can mitigate well instabilities that associated with problem during drilling. Please note the stability analysis uncertainty funnel. If we look at the upper part of the funnel, we can see that the problem of incorrect mud weight, incorrect trajectories, incorrect drilling technologies, and the uncertainty of geological structure of the formation. Misunderstanding of stress distribution, chemical activity of rocks, stress changes allow poor wellbore cleaning, this is all lead to sticking, loss of circulation and cementation problem. As a result, the cost of this well increased, non-productive time increase and drilling speed decrease. Therefore, stability analysis is always a complex job. The types of wellbore instability typically include chemical instability and mechanical instability. The chemical instability is associated with the chemical activity of rocks, and the most active rocks are clays because they are capable of reacting, for example, with the mineralized water. The second type of instability is a mechanical instability. As a rule, this is everything that is related to the stresses, elastic and stress properties. That is a classical understanding of the problem of reservoir geomechanics. In this presentation we will consider commonly mechanical instability. This is topic number 2, borehole failure type and their identification. The depending on the mud weight that is used during drilling, the behavior on this wellbore must be different. If the mud weight is lower than pore pressure, then blowouts or fluids will be observed in the fluid saturation formations. If the mud weight is higher than the pore pressure but lower than collapse or shear failure pressure gradient, then this will be breakouts maybe, or collapse will be formed. Another name is called as shear failures, which when drilling well is manifested by the big amount of cuttings. This is fragment of drilled rock that have a specific splintered appearance. The shape of these fragments we will talk later. Accordingly, if the mud weight is higher than the collapse pressure of the formation and lower than losses pressure, then this is called a safe mud weight window. The well will be stable here and have a predominantly round radius whose diameter is equal nominal diameter of bit. If the mud weight exceeds the loss pressure equal to the minimum horizontal stress but lower than the breakdown pressure, in the presence of the existing failures or faults, the reactivation of these failures or faults will be observed, with the subsequent losses of drilling fluid into the formation. Finally, in the extreme cases, the mud weight exceeds the breakdown pressure. Then in this case it's assumed that a crack will form. Its opening and the complete absorption of lost fluid into the formation. Please pay attention on the main types of well failures. Primarily, this includes breakouts and drilling-induced fractures. The breakouts are formed in the rock strength is below the hoop stresses. The breakouts are formed in the direction of minimum horizontal stress. The tensile fractures form if a hoop stress is less than tensile strength. It's formed in the direction of maximum horizontal stress. The images are the best tool for identification such well damage. If the image picture the breakouts look like white stripes, but the fractures are narrower than their breakouts. But it's important to pay attention to the fact that not all destruction are well as breakouts. That is, not all destruction is a consequence of rock mechanics. For example, if you pay attention on this slide, during the chemical interaction of the clay walls of the well and the drilling fluids, washouts can be formed that are not in the strict sense as breakouts. Okay? There are complex failures in the form of both breakouts and washouts. But also in the case of overpulls or landing of the drilling tools, one-sided cases can be formed, which are presented as a one-sided anomaly on caliper measurements. This slide shows an example of the difference between cavings, cuttings, which are formed as a result of collapsed and ordinary drill sludge. The left figure shows cavings that have a specific angular, plate-shaped or fragmented morphology. Cavings may appear during drilling and after flushing, after tripping, after backrimming out of hole. Normal sludge is in the form of neatly drilled rocks, and thus differences between cavings and sludge must be taken into account when analyzing borehole stability. Some of the subsequent slides show the excellent work of Mohr and colleagues in 2012, in which they carried out a complete analysis of stability of the wellbore with analysis of the shape of the cavings. and 4-inch interval photographs of the cuttings are shown on this slide. In this figure, for above section, we see that the cavings have the splintery and angular morphology, which in general is generally confirmed by the geomechanical model, which shows that the gradient of pore pressure and collapse almost reach the mud weight. The next slide clearly shows that the collapse gradient reached the drilling fluid mud weight, and we see an angular, blocky, platy shape on the cavings. Take a look at the interesting slide. In the case number 1, we don't observe any cuttings because in this interval the mud weight density increased that completely compensate the wellbore. But as soon as we go lower in cases 2 and 3, the pore pressure and collapse pressure gradient are again observed to approach the level of equivalent circulation density, and the many cuttings again take on angular blocky shape. On the next slide, almost all cases the same picture is observed. We also see different color, visible bedding planes, sharp edges, blocky and angular fragmented, that indicates on hole may be having words of instability. The same goes as next section of this well. But even in the last section of the well, due to the fact that the equivalent circulation density is much higher than the pore pressure and collapse pressure, there are no cavings. Thus, we can conclude that working with photographs of cutting, their shape and morphology is one of the most valuable information for calibration of geomechanical model. At the beginning of the presentation, I said that we would consider mainly mechanical instability, but I suggested just a few words about chemical instability. The destruction of clearly rocks occurs in 2 stages. The first stage is absorption of water by clay and the consequent swelling of clay. And second type, this is dispersing hydrated clays particles. This is source core material that not wetted with a dispersion medium. This core etched in fresh water. This core matured in a reservoir water that presented a dispersion medium with a mixture of inorganic inhibitors, sodium, calcium and potassium chloride. At last, this core matured in the dispersion medium with this mixture of inorganic inhibitors, reservoir water containing sodium, calcium, potassium chloride salts, and an organic inhibitor, one of the test subjects. Based on the research result obtained, it can be stated that clay hydration is maximally prevented by combinating of introducing of organic and inorganic clay inhibitors into drilling fluid. Preventing the dispersion of clays and their entry into the drilling fluid will thereby reduce during well construction the likelihood of technological accidents and incidents that often occur during the passage of wellbore instability intervals. That's represented by clay deposits prone to hydration. Based on this slide, we can conclude that horizontal wells are worse drilled due to their trajectory. The sludge and cutting deposit directly to the bottom of the wells and make difficult the clean hole. Therefore, drilling at deviation greater than 50 degrees is difficult on terms of clean hole. This is examples of trouble plot. This trouble plot shows the main drilling events It can be used for geomechanical model calibration. The topic number 3 is borehole stability elastic solution for any well trajectory. In this topic we will consider how we can calculate shear fracture gradient and breakdown gradient. Drilling itself is the formation of mine working. This mine may be stable or unstable. In order to accurately answer this question, a physical and mathematical model is needed that would describe under what conditions it's unstable. This is especially important for the construction of oil and gas wells, because instability of wells greatly increases the cost of drilling. The main factor of instability are rock strength, high pore pressure, chemical interaction, and well trajectory. Next, we will look at the steps by which you can evaluate the stability of wells. Borehole stability modeling for drilling operation is primarily to quantify a safe mud weight window, such that the design mud density will be higher enough to ensure borehole stability and lower enough to not fracture the formation. Therefore, the mud weight window should be greater than the pore pressure gradient and shear failure gradient and less than fracture gradient. To determine the shear failure gradient, the first step is to analyze near-wellbore stress distribution induced by drilling. It's commonly assumed that in situ or far field stress consists of 3 mutually orthogonal principal stresses: vertical stress, minimum horizontal stress, and maximum horizontal stress. It is also assumed that the subsurface rocks are in situ stress state before drilling. To continue considering the calculation of the stable state of wells, it's necessary to introduce some assumptions. At first, we believe that rocks are homogeneous. Second, it's assumed that we know vertical stress, SH min, SH max. Also, we usually know SH max very purely. Yes. Knowledge of cohesion, angle of internal friction angle, Young modulus, Poisson's ratio, and we will consider that pore pressure is constant. So the borehole can be imagined as an opening in a plate as shown in middle picture. When the well deviates if any angle and azimuth, this borehole face will rotate accordingly. For any orientation of the well, it's necessary to calculate the stress state corresponding to this orientation. The hole possesses inner and outer radius so large compared to inner that they can be deemed infinite. Two solutions can be have surfaced for this dilemma: the isotropic and anisotropic solution. Our focus will be on the anisotropic solution. Step number 1, it's identification of principal in situ stress state. Step number 2 is definition stress state with respect to the Cartesian coordinate system attached to the wellbore. At last, state number 3, find out the stress state with respect to the cylindrical well coordinate system. As previously mentioned, we assume that the input stresses represent the principal in situ stress, vertical, maximum and minimum horizontal stress. Given that the wellbore can have any orientation, the stresses need to convert to new Cartesian coordinate system x, y, z outlined in step number 2, where stresses S0x, S0y and S0z are defined. The orientation of the new stress component are determined by the wellbore's inclination from vertical geographical azimuth and the wellbore's deviation from x-axis. It's important to highlight that in this transformation the y-axis is always a line parallel to plane defined by SH max and SH min. Previous equation can also be shown in matrix format. After finalizing the result of stress transformation, we can proceed to address step 3 within the analysis methodology pertaining to the anisotropic solution. This solution will be further elaborated in subsequent topics. Frequently, variations exist in normal stress across different directions, leading to the emergence of shear stress and their associated shear strains. This signifies that both strains and stresses must exhibit continuity throughout the body without any change. Typically, this is managed by introducing a stress function. From a mathematical perspective, the strain functions need to have continuous partial derivative to meet the compatibility requirement for a plane problem formulations in polar coordinate system. In the absence of body forces, a function that satisfies the compatibility equation is given by the following relation between the Cauchy stresses and area stress functions. A general solution to the previous equation in polar coordinate system is shown in this slide, where SRR, this is radial stress, S theta theta, hoop stress. The boundary condition will be defined below the different loading scenarios. The figure shows the external stresses decomposed into an arbitrary orientation. Each of these will first be solved for individually and the solution will be superimposed. And from previous equation, the following stress components are found as shown here. Upon revising the equation presented in previous slide, we recognize that the outer boundary condition comprises two components, hydrostatic and deviatory. In the forthcoming solution, we intend to dissect these components, address them individually, and subsequently combine them to determine the solution ultimate. Taking into account the accepted boundary values, the following equations are obtained. This set of equations is known as the Kirch equations. R lowercase is inner radius. R uppercase is outer radius. In case of inner and outer radius equal, the distribution of near-wellbore stresses on the well wall will be obtained as shown on this slide. This is example of near-wellbore stresses distribution around the well if the inner radius and outer radius are equal. This is example of far field stress distribution. These figures show stereo nets of near-wellbore stresses, circumferential or hoop stress, radial stress, axial stress, and their changes depending on the initial parameters, true vertical depths, azimuth, deviation, overburden gradient, pore pressure gradient, minimum maximum horizontal stress gradient, azimuth of horizontal stress, mud weight, Poisson ratio, Biot poroelastic coefficients. Okay, when induced stress at the wellbore well exceed the rock strengths UCS, the wellbore start to fail. The Mohr Coulomb failure criterion can be used to determine wellbore shear failure. In shear failure condition, the applied mud weight is low and radial stress equal mud weight. Therefore, effective radial stress can be assumed as minimum effective stress. After we have equated the effective minimum maximum stresses, the minimum mud pressure to prevent shear failure around the wellbore well for inclined borehole can be obtained from the following equations that you see on this slide. The maximum extremum on this function is the desired value of shear failure pressure. By solving this equation, we answer the question of wellbore wall stability. That is, the stability of the wellbore wall is a function of applied drilling fluid density or mud weight, stresses, strengths, elastic properties, as well as the well trajectory. And so then, let's discuss about UCS. In one of the last lectures, I gave the classification of rocks according to their unified compressive strengths, unconfined compressive strength, sorry. This lecture I am reapplying it just to remind you. Please note that the weakest rocks, and therefore the rocks that are most susceptible to shear failures are weakly consolidated clays, sandstones, rocks of fault and contact zone, weathered rocks. So the moderate stability is characterized by cemented sandstones, siltstones, as well as carbonate rocks and marls. The strongest stable rocks are those of igneous and metamorphic rocks. For example, this granites, dolerites, diabase, quartzites, etc. This slide showed the calculation of another component of the stability analysis, but not a shear type, but a tensile one. That is called breakdown pressure. That is, this is the beginning of the initiation of tensile cracks. This parameter, as well as the pressure of shear failures, depends on well trajectory, strengths, elastic, and stresses. And when solving this equation, the breakdown pressure will be minimum extremum. As viewed in S1, S2 and S3 space, the yield surface of linearized Mohr Coulomb criterion is right hexagonal pyramid equally the inclined into the principal stresses axis. The intersection of this yield surface with the p-plane is a hexagon. The p-plane is the plane perpendicular to the straight line S1 equal S2, S2 equal S3. In addition to the criterion of Mohr Coulomb, there are some other criteria. We will consider them in following lectures. On this slide, I would like to show that the calculation of well-bore wall stability looks like. By calculating the stability of variable walls, I mean the calculating of pressure of shear failure and tensile failures. On this slide, they are shown in yellow and dark blue field. Pore pressure, minimum horizontal stress calibrated to the actual pressure measurements in wells. Shear failure pressure is calibrated to the drilling events, as overpulls, landings, and increased volumes of cavings. The next topic is borehole stability depending on deviation and azimuth of well. The main purpose of this and following slides is to demonstrate that shear failure pressure and tensile pressure depend on the well trajectory, while pore pressure, overburden pressure, and minimum and horizontal stress doesn't depend on the trajectory of well. Okay, losses and breakdown. In addition to stress, elastic and strength properties and well trajectory, it should be known that the stability of well bores is a function of a time. Please pay attention to this and the following slide. We see that in the same well, in the same interval, caliper measurements during drilling and calipers after 2.5 hours and after 15 minutes. On the next slide, are significantly different. Sorry, not 15 minutes, 3 days after drilling. Caliper with a time delay show breakouts, that is shear collapses. This means that time must also be taken into account when analyzing stability, and reducing open hole time is key objective. Please pay attention to this slide. Here are two calipers. First caliper is caliper wide drilling, and second caliper is back reaming out of hole caliper. During drilling, we practically don't observe any breakouts or collapses because drilling is controlled by a high value of equivalent circulation density. During back reaming out of hole, the calculation density decreases to the static level, and accordingly breakouts are formed. Here it's one again confirmed that stability is a function of the time. And this slide shows another example of how static density of drilling fluid affects the stability of the well bore. Note that the wells 1 and 2 were drilled with lower mud weight, while wells 3 and 4 were drilled with higher mud weights but exhibited fewer cavities and kickouts. Here and below, shear failure gradient steeriness is shown. Clockwise azimuth shows distance from the center of the circle shows the distance from well bore. Please note that how the pressure of shear failure increases with decreasing strength. That is, the weaker the rocks, the more leads will not form, and the more there will be championship. This slide shows shear failure gradients, maps of shear failure gradients for different well trajectories. The well trajectory is shown on the stereonet of the top right. Notice how the shear failure gradient increases in well with extended reach from the vertical in the direction of maximum horizontal stress and perpendicular to maximum horizontal stress. The most unstable wells are predicted in the direction of maximum horizontal stress. The next topic is borehole stability in case of any stress regime. Now let's consider the dependence of the borehole stability on the stress state mode. Recalling that there are three modes of stress state: normal fault, strike slip and reverse fault. For normal fault, the greatest stability is typical for vertical well from wells with a slight deviation from the vertical in the direction of minimum horizontal stress. The most unstable wells will be horizontal wells drilled into the direction of maximum horizontal stress. This is schematic well in normal fault. In case of strike slip, vertical wells will be most unstable. The most stable will be horizontal wells drilled in the direction of the minimum horizontal stress. Please note the scheme of well during strike slip. With the reverse fault, the situation will be opposite to the normal fault. The most unstable well will be horizontal wells drilled in the direction of the minimum horizontal stress, not maximum horizontal stress. Now let's look at the potential geometry of fractures that will form during hydraulic fracturing. If the well is drilled in the direction of minimum horizontal stress, then during hydraulic fracturing, a hydraulic fracture will form perpendicular to the wellbore. There will be multiple fractures. Under normal fault and in horizontal well drilled in the direction of maximum horizontal stress, a hydraulic fracture will form parallel to the wellbore. As a rule, it will be a single fracture. A single fracture will be formed while in the case of vertical well. In intermediate cases, there will be formed reorientated multiple fractures away from well. The next topic is borehole stability uncertainty analysis. In order to reduce uncertain risk for project well, as a rule, a drilling risk analysis is prepared. It consists of describing in as much detail as possible each potential problem that may arise during drilling and the drilling process. As a rule, this is associated with stickings, collisions, gas shows, and other drilling events. Here are shown the three cases of a geomechanical model, so that drillers have not one density value but some range. This is low case, base case, and high case. Now we are slowly moving on the analyzing the sensitivity of the initial parameter to the final result. In this case, we will consider the influence of initial delta on the shear failure gradients and fracture gradients, breakdown gradients. So, to do this, you first need to set the uncertainty range of the initial parameters, namely inclinometry, elasticity modulus, strength properties, stresses, etc. In this case, the uncertainty range was determined using histogram on basis of which the values P10, P50 and P90 were found. Accordingly, the extreme values of uncertainty were P10 and P90 each. Next, several thousands shear failure gradient calculation are carried out, after which a tornado plot and spider plot are built, which shows which initial parameter have the maximum impact on the spread of shear failure gradient. Next, we will consider the sensitivity analysis of the initial parameters on shear failure gradient for various types of wells: vertical, inclined, horizontal, depending on the type of stress-strain state: normal fault, strike slip, and reverse fault. Ultimately, we will have 18 graphs for the breakdown gradient and shear failure gradient. There are tornado plots for normal fault, strike slip, and reverse fault for shear failure gradient for vertical well. This is breakdown gradient tornado plots. There are tornado plots for normal fault, strike slip, and reverse fault for SFG for inclined well. In this case, we will see that most contribution have the overburden gradient instead of maximum horizontal stress, as they are shown in previous case. Okay. This is breakdown gradient tornado plots. There are tornado plots for normal fault, strike slip, and reverse fault for shear failure gradient for horizontal well. And this is tornado plot for a breakdown gradient in horizontal wells. And at the end of this topic, we will provide an analysis of Monte Carlo uncertainty. The essence of this analysis is to find the most reliable values for the safe drilling window. First, as in the previous case, the uncertainty range of the initial parameter are estimated. As a result, instead of tornado plots, cumulative shear failure gradient histogram are constructed, and the intersection of these cumulative histograms in the interval P90 is found. This intersection will be most likely safe range of drilling fluid density. At last, the final topic is borehole stability calculation in LithoStudio. This is a link and QR codes for lessons of calculation of borehole stability analysis in LithoStudio software. Please go to the link and continue the work with LithoStudio software. This is references that used while preparing of this lecture. And this presentation made with SlidesGo templates. Thanks SlidesGo. Thank you so much. Goodbye.